High Temperature Gas-Cooled Small Modular Reactors by Vanessa Peppers. Between 2009 and 2020, renewable and nuclear sources recognized as efficient carbon-free alternatives emerged as the fastest-growing energy source, achieving an annual growth rate of 13.4% and accounting for nearly 29% of global electricity generation by 2020. Nuclear and renewable energy play a vital role in decarbonizing the energy sector each year. As zero-emission sources, they are key drivers in the global shift toward carbon neutrality. The International Atomic Energy Agency classifies nuclear reactors with capacities under 300 megawatt electric as small. While the concept of compact reactors isn't new, having been used in naval submarines for over 50 years, small modular reactors bring a fresh approach. Modular refers to their prefabricated components, which can be built off-site and assembled quickly on-site. With a compact footprint, SMRs are particularly well suited for areas where traditional large-scale nuclear plants are impractical. High-temperature gas-cooled reactors, HTGRs, are advanced nuclear systems recognized for their high thermal efficiency, strong safety features, and diverse application potentials. The differences between HTGRs and light water reactors include coolant and moderator, operating temperature, fuel type, safety features, applications, and efficiency. HTGRs use helium gas as coolant and graphite as moderators, while light water reactors use light water as both coolant and moderator. Operating temperatures for HTGRs range from 750 degrees Celsius to 950 degrees Celsius. Light water reactors operate at much lower temperatures around 300 degrees Celsius. HTGRs employ triso fuel particles, while light water reactors use UO2 fuel rods clad in zirconium alloy. HTGR safety features are designed with passive safety in mind, while light water reactor relies on more of an active safety system. HTGRs can be used for electricity generation, hydrogen production, desalination, and industrial process heat, while light water reactors are only used for electricity generation. The efficiency of HTGRs is significantly higher than light water reactors, which have an efficiency of around 33%. The idea of a high-temperature gas-cooled reactor was first proposed in 1944 by Farrington Daniels. During the 1960s, Peach Bottom Unit 1 began operation in the United States, and Dragon Reactor began operation in the United Kingdom. And during the 1970s, AVR began operation in Germany, and Fort St. Vrain began operation in the United States. From the 1980s to 1990s, interest waned due to economic and regulatory challenges. However, in the 2000s, renewed interest in HTGRs began as part of Generation 4 reactor initiatives. In the 2010s, HTR-10 began operation in China and HTTR began operation in Japan. From the 2020s to present, HTR-PM began operation in China. X Energy's XE100 advances toward deployment with the United States Department of Energy support. HTGRs feature two primary core designs, each with distinct structural and operational characteristics. In the prismatic block design, triso fuel particles are embedded in cylindrical fuel compacts, which are then inserted into hexagonal graphite blocks. In contrast, the pebble bed design uses spherical fuel elements, each about the size of a tennis ball, containing triso particles dispersed in a graphite matrix. Triso fuel, short for tristructural isotropic particle fuel, is one of the most advanced and resilient nuclear fuels ever developed. Each triso particle contains a tiny uranium fuel kernel surrounded by three protective layers: inner pyrolytic carbon, a ceramic silicon carbide barrier, and an outer pyrolytic carbon shell. Helium is used as a coolant because it's chemically inert, neutron transparent, and remains in a single phase across the reactor's operating temperature range. Helium circulates through the reactor's core, absorbing heat from the fuel and transferring it to a heat exchanger. High-efficiency circulators maintain helium flow throughout the core and heat exchangers. Heat moves from the trisol fuel particles through the graphite matrix to the helium coolant. Helium gas carries the heat away from the core to the heat exchangers. At high temperatures, radiative heat transfer becomes significant. Trisol fuel can withstand temperatures exceeding 1,800 degrees Celsius without structural failure. A hallmark of HTGRs is their passive safety. The combination of low power density, high heat capacity materials, and durable fuel design helps prevent overheating, even without active cooling systems. In the event of a loss of active cooling, HTGRs are designed to passively dissipate decay heat. The trisol fuel particles and passive heat removal systems combined with graphite moderation and helium coolant make HTGRs resistant to core meltdown. Many HTGR designs are modular, allowing for factory fabrication, shorter construction timelines, and flexible siting, even in remote or industrial locations. This modular approach allows utilities to scale capacity incrementally based on demand, budget, or site constraints. It also shortens construction timelines and reduces upfront capital risk. HTGRs can operate in various modes, including baseload and load following, making them compatible with grids that incorporate intermittent renewables. Their high outlet temperatures enable not just electricity generation, but also industrial applications like hydrogen production, desalination, and synthetic fuel synthesis. This versatility allows HTGRs to serve both power and process heat markets and is due to the reactor's high thermal inertia, robust trisol fuel, and advanced control systems. HTGR capital costs vary depending on configuration and scale. For example, a single 350 megawatt thermal HTGR using a Rankine cycle was estimated to have a capital cost in the range of $4,000 to $6,000 per kilowatt electric, with operating and maintenance costs influenced by staffing and fuel cycle assumptions. Modular designs can reduce per unit costs through economies of scale. These applications are especially attractive in regions with high fossil fuel costs or carbon pricing mechanisms. HTGRs become economically favorable when natural gas prices exceed $7 to $10 per million BTU, carbon pricing or emission penalties are introduced, or when industrial sectors seek high temperature, carbon free heat sources. HTGRs produce virtually no CO2 during operation, making them a strong candidate for decarbonizing electricity and industrial heat sectors. Modern HTGR designs aim to reduce waste generation through optimized fuel utilization and longer core lifetimes. Modular designs also help limit the scale of decommissioning waste. Unlike light water reactors, HTGRs use helium gas as coolant, eliminating the need for large volumes of water. This makes them especially suitable for deployment in arid regions and areas with limited freshwater availability. Key industrial applications of HTGR process heat. HTGRs can drive thermochemical cycles or high temperature electrolysis to produce clean hydrogen at scale. They can supply the heat needed for converting coal, biomass, or natural gas into synthetic gasoline, diesel, or substitute natural gas. HTGRs can replace fossil fuel derived heat in ammonia synthesis, reducing CO2 emissions in the chemical industry. Coupling HTGRs with multi-effect distillation or reverse osmosis systems enables efficient freshwater production in arid regions. HTGRs can provide steam and heat for bitumen extraction and refining processes, displacing natural gas. According to the OECD Nuclear Energy Agency, HTGRs are among the most promising Generation 4 technologies for industrial heat applications. Several high-temperature gas-cooled reactor projects are either operational or under development around the world. HTRPM in China, XE100 in the United States, HTTR in Japan, HTR10 in China. Top companies in HTGR development are X Energy in the United States, China National Nuclear Corporation, Japan Atomic Energy Agency, General Atomics in the United States, and UK National Nuclear Laboratory. Key research institutions and initiatives include the Idaho National Laboratory and the U.S. Nuclear Regulatory Commission. The OECD Nuclear Energy Agency also coordinates international collaboration on HTGR technology, focusing on licensing, safety, and industrial applications. HTGRs differ significantly from light water reactors, so existing regulatory frameworks, largely built around LWR assumptions, must be adapted. This includes redefining safety margins, containment strategies, and emergency planning zones. Because HTGRs are relatively new in commercial deployment, regulators have less empirical data to validate safety models, fuel performance, and accident scenarios. This makes it harder to establish a robust licensing basis. HTGRs rely heavily on passive safety features and low source terms, which challenge traditional deterministic safety analysis. Regulators must integrate probabilistic risk assessments and develop new criteria for equipment classification and event selection. HTGRs also require specialized components with limited vendors, which can delay deployment. Most people are unfamiliar with HTGR specifically, and nuclear energy in general often faces skepticism due to historical accidents and waste concerns. Public outreach and education will be crucial to improving understanding and acceptance. Public opinion is also shaped by national energy policies, media narratives, and endorsements from trusted institutions. Countries that frame HTGRs as part of a clean energy transition may see more favorable public sentiment. High-temperature gas-cooled reactors are poised to play a pivotal role in the clean energy transition thanks to their unique combination of high thermal efficiency, inherent safety, and industrial versatility. Countries like China, the United States, Japan, and the UK are actively investing in HTGR development. The IAEA has identified HTGRs as one of the most advanced and ready Generation 4 technologies. Future advances in reactor design include ultra-high temperature capability, digital twin and AI integration, and hybrid energy systems. In short, HTGRs offer a clean, scalable, and flexible energy solution that bridges the gap between electricity generation and industrial decarbonization.